All right, that's going to be it. So I'll be looking for at least one of these done correctly. All right? If they're, well, I'm going to have to see how the whole class does. If you're the only one who got them both right, you're going to get some bonus for that.
Oh, the homework is
You keep the homework. I just want the quiz. That's all I want. Anybody else with the quiz? It's what?
It just clicked.
Oh, you just got it? All right. All right, is there anybody else that needs to turn the quiz in? All right. The answers to both of these problems are on the web already. I made the video that shows how to work all the even problems, so I'm not going to work through these right now. All right? You can go watch them if you want them. The substitution though on that first one was what?
square root x.
U was root x, and over here? Pi over x. So
What's pi over x in those two?
the derivative of pi over x is negative pi over x squared.
And that, that's where I got the
Okay, now I will address any questions over the homework. I know some of you said I was doing okay, but then I got kind of hung up at the end.
47?
47. How many people have problems with 47?
Yeah, 45, 47.
Can I use this? Because I didn't even think about it, but I have the other last book, and I just did it because I didn't.
Can you use that what?
On the quiz.
Well, we just took the quiz.
I didn't realize I had it.
Oh.
I'm being like.
Well, you were allowed to use your homework from what you just did, 5.5.
From the last book. That's why, like.
Yeah.
And then I got the new book.
Well, not now. It's already. Yeah, it's done. Okay. So what was it? 40? How many? 45.
45, we can start there.
45. Well, I only can only do so many today. 45. 47.
I just skipped.
Okay, let's do 45 first then. So for 45 we have all right, so the challenge I guess in this one is perhaps that it's not easy to see something in its derivative necessarily here. We see an x minus 1, we see a root. This x by itself, we never let u be x, right? So I need something a little more than x. I could go maybe x minus 1. I could do the whole root, but the derivative of a root's pretty complicated, so you know it would make, I don't have anything really complicated in there other than the root itself. So maybe just x minus 1. And then the derivative of that is just dx, right? So I've got dx right here. I can replace that with what? du. I've got this right here, which I can replace. That'll become square root of u. And then the x, though, is the problem. But I can take this equation and solve it for x by adding 1 to both sides of the equation. Right? This was like that problem that we did that was like raised to the 70th power. And we did that little thing in there. Okay. So this integral becomes, our new integral becomes integral of x, which is really u plus 1, times the square root of u du. And this u plus 1 needs to be in parentheses. And then this square root of u is really u to the 1/2 power. So you can distribute that through the parentheses. So it becomes square root u to the 3/2 plus u to the 1/2 du. Does that help? Like u to the 1/2 times u is u to the 3/2. U to the 1/2 times 1 is u to the 1/2. And then power rule on each of those. Is that all right?
Yes.
Do you want me to keep going, or?
Yes.
Yeah? Okay, so now, what's the antiderivative of u to the 3/2? I mean, did I say derivative or antiderivative? I said derivative? I'm sorry. What's the antiderivative of u to the 3/2? 2/5 u to the 5/2. So that becomes 2/5 u to the 5/2 plus 2/3 u to the 3/2 plus a constant, right? So I'm doing the indefinite integral first, then I'll do the definite. So now I replace my u, right? Don't forget this step. Your u is x minus 1. So this becomes 2/5 x minus 1, to the 5/2 plus 2/3 x minus 1 to the 3/2 plus c, right? Yes?
I'm just trying to see what you got for 3/2. You get 3/2.
This right here is u to the 1/2, right?
Yeah.
When I multiply that times this is a 1. I have to add exponents. 1 plus a half is 3/2.
Yeah, it's not doing more sense.
So now at this point, I'm ready to do the definite integral. So the original problem becomes this, right? Evaluated at, what are the two endpoints? 1 and 2, right? So just save time and space, I'm gonna do what I would do next line. I would put the 1 and the 2 here like that. And then I'd plug in 2 first, then subtract what I get when I plug in 1. So let's plug in 2 first. I have 2/5, well, first of all, big parentheses here. I have 2/5, and then when I plug in 2, right, 2 minus 1 is 1. 1 to any power is 1, so that's just going to be a 1. Plus 2/3, same story over here, right? That's 1 to the 3/2, that's 1 again. Minus, now plug in 1s, it's even better, isn't it? What do you get when you plug in 1 here? 0, 0, so you just get a bunch of zeros over here. So it should be 2/5 plus 2/3, right? Which is 16/15. 16/15. Does that help? Okay. So what was the problem then? What hung most of you up on that one?
It was distributed, and I got that whole part up until the point where you distributed n to the u. When you have
Oh, the u to the 1/2 into the other two? Okay.
I didn't do that. I just did this.
So you tried maybe another substitution? Oh, yeah, that could have been bad. Okay. All right. What about another one? Some people mentioned 47.
Nah.
Okay, what else then?
Yeah, e squared.
Everything else was good? Yes? Which one? 51? Integral e to the 4th dx over x square root natural log x. So do you see something in its derivative? Yeah. If I rewrite this as 1 over the square root of natural log of x times 1 over x dx, all I've done is I pulled the dx way out. This x on the bottom, I pulled it out as a 1 over x. And that's great because the derivative of natural log of x is 1 over x. So now I see something in its derivative there. Do you see that? And now my natural substitution here would be u is natural log x. Du is 1 over x dx. I have that exactly right there. Right, that matches up. That's my du. This is going to be my u. So what does that integral become? What is it?
It's 1 over u.
1 over root u, right? 1 over square root of u, which is the same as 1 over u to the 1/2, which is the same as u to the negative 1/2, isn't it? So I'm going to do all that in one step. I'm just going to write u to the negative 1/2. And then du. And now I can go straight to power rule. 2u to the 1/2. So that's the antiderivative using the power rule for integration. 1 over n plus 1, u to the n plus 1. And then now for this, replace my u, right? So this is 2 natural log x to the 1/2 plus c, right? And this was a definite integral. I'm supposed to plug these in, right? Supposed to plug these in? So here's where I am. I'm taking 2. Guys, I don't mind y'all talking, but if I can hear you, everyone can, and it might be somewhat distracting to other people, okay? So there's my antiderivative. There's my 2 limits of integration. And they picked really nice limits of integration, didn't they, for us? Because when we plug this in, we get, first of all, 2 natural log of e to the 4th, and then all of that square, or to the 1/2, which is square root, minus 2 natural log of e to the 1/2. So what's natural log of e to the 4th? That's just 4, right? Natural log and e basically wipe each other out. They're inverse functions. And so you just get a 4 here. What's 4 to the 1/2? 2, that's square root of 4, and then 2 times 2 is 4. So that's a 4 minus natural log of e is 1, because that's a 1 up there, right? So 1, square root of 1 is 1, 2 times 1 is 2. So you get 4 minus 2, which is 2. What's that?
It's funny how all that mess is 4 minus 2.
Yeah, I know. Well, they have to make it real. Well, they try and make it where the numbers work out to be pretty clean for us right now.
Oh, okay.
Later on, the numbers aren't necessarily going to be nice. Yes.
You get 4 on the left side again?
I'm using just this property. The natural log of e to the x equals x. That any time you have natural log composed with its inverse function, which is e, that they wipe each other out and it just returns the x.
Okay. Element is 1, you bring the x to the front
You could look at it that way also. You could bring the x out front,
and have x.
and then natural log of e is 1. But the reason why natural log of e is 1 is because there's a 1 out here, and these are going, it's 1. So, I mean, either way you want to look at it.
So could I do that?
Sure.
Bring the x to the front?
Yep, that's fine. Hey, just little question about logs here. We have that property that you were talking about, bring the thing out front. Can I just bring this 1/2 out front here and make that 1/2 times the 2?
Yeah. I guess so. No.
If no, why not?
It doesn't seem right.
It doesn't seem right?
It will work out though, right? 2 over 2 is 1, and then it's 4. It defies my natural instinct.
Because here's the rule for pulling those powers out. The power can come out in front, right? That's what you've been taught. It actually saved our butt quite a bit in Cal 1 to be able to do that. But the n has to be acting on the x. So this power is acting on the argument, that's the thing being plugged into the natural log. So you're raising the argument of the log to the n power. Here, the argument is x, but it's not being raised to the 1/2. It's the natural log function that's being raised to the 1/2. So that 1/2 cannot come out. That's why that parenthesis around here is so important. Because if I don't have that parenthesis there, You might think that means, oh, take the square root of that first, then the natural log. That's not the way you're supposed to do it. Okay. All right, let's keep rolling. So the substitution 5.5, we are putting it behind us now. And we are moving into chapter 6. And chapter 6 is titled Techniques of Integration. Did I spell techniques right?
Yeah.
You ever look at a word and it just doesn't look right sometimes? Techniques, is that right? Okay, so techniques of integration. We already have learned, we've been integrating, right? Finding antiderivatives was the act of integration, that's what it's called. So now we are going to come up with some techniques. We already have a couple. Most importantly, substitution. That is our first major technique of integration. We could have thrown it into this chapter, but this author chose not to. They introduced substitution earlier. So our first technique in chapter 6, which is actually our second real technique, is called integration by parts. 6.1. Integration by parts. Now, I'd like to just take a quick poll because I know there are some of you who have seen Cal 2 before. Either you've taken the class and are retaking it, or you saw it in high school or something like that. How many of you that feel comfortable have seen integration by parts before? I just want to have an idea of who has and who hasn't. 1, 2, anybody else? Okay, all right. Maybe then you can tell me after you've seen it, okay? Because the further we go along, the less people should have seen. So hopefully we'll get to a point where this is fresh for everyone. So right now, if we're looking at an integral and we see something and its derivative, maybe we can get it, right? By substitution. If we see something and its derivative, then we go u equals and we try this stuff, right? Go for it, but it doesn't always work. So let's take a look at a problem like this. Integral x cosine 2x. Yeah, let's go 2x. Well, you know what? Make it 5. That way people aren't trying to do some double angle identity or something on that.
Well, you did 2x?
I had 2x, but then I was afraid people would be going trying to do double angle identity. All right, so when we look at this, let's try with what we have so far to attack this problem. We try and find something in its derivative. Well, do you see something in its derivative?
Kind of.
Kind of, right? If we choose u to be 5x, the derivative of that is what? 5. We're off by a constant. That might work. So let me try it. U is equal to 5x. du is equal to 5dx. And I have dx here, so I can multiply both sides by 1/5. And that means I could replace my dx with 1/5 du, right? So far, this is going to be a u. This is going to be a 1/5 du. What don't I have yet?
Yes.
I don't have the x. But this right here, don't we? Okay, so let's go with that. So what would we have here? 1/5 u equals x. So I'm all ha 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 ha, got it, you know? Sneaky, sneaky me. So I come back through and I rewrite the integral now. What are you going to have? And let's just write them in here. 1/5, I'll pull the constants out in a second. Cosine of u, and then 1/5 du. Pull all your constants out. 1 over 25, integral u cosine u du, right? What's wrong?
Kind of the same situation.
It's kind of the same thing, isn't it? I mean, we had an x and we had 5x in there. We've turned it into a u and a u, but we still don't have a formula for that, do we? And worse than that, what would you pick for substitution now? Like even if you tried another substitution, like a double substitution on this problem? You have, I mean, u's pretty much your only choice, isn't it? I mean, you could go cosine u, but then derivative of that is negative sine u. You don't even have it here, right? So you kind of like run out of things to choose, haven't you? So substitution isn't going to work. So there's got to be a way to get this answer, right? I mean, maybe. So the reason for this example to start this is to show you that substitution does not give you the ability to integrate everything. That's why you need other techniques. Integration by parts is the first one, second after substitution, that I'm going to show you. All right? Now, integration by parts, I'm going to show you where it comes from, then I'll give you the formula. All right? Recall from Cal 1 that if I have two functions, I'm calling them u and v, all right? Now you could, maybe in Cal 1 you like to call it like f and g, right? A function f and a function g, and you multiply them. Then if I took the derivative of this, you had to apply the product rule, didn't you? And so the product rule said, well, depending on how you were taught, maybe you were taught it's the derivative of u times v plus the derivative of v times u, or some variation of that, but it should be that. You should have a derivative on the u, no derivative on the v, plus the other one should have a derivative on the v and no derivative on the u, right? Now the way I want you to write it, just to help derive this formula, is I want you to write it as, and I'm going to write this left side like this also. Write it as v u prime plus u v prime. So that's the same thing, isn't it? I just flip those two over. So the primes represent the derivatives, right? The derivatives. So I'm going to now do something on both sides of this equation. I'm going to take the antiderivative on both sides. Right? So let's see what happens. If I take the antiderivative, that means I want you to find the integral. Integral here. So I'm taking the antiderivative here, right? So that's just this. Equals, now antiderivative here, since it was addition, I could do the antiderivative of each one. Does that make sense? Now, what do you think the antiderivative of the derivative does? So it's kind of like clean the car, then make it dirty, right? Start with a dirty car, clean it, make it dirty again, right? The derivative, if I say, take the derivative of this, but then undo that, what would you get over here? U times v, right? U times v. U times v. Now over here, you can't do that because the derivative is only sitting on one of them, isn't it? Like the derivative is only on the u, and here the derivative is only on the v. Here the derivative was on the whole thing, so it was like, wash it, make it dirty, whatever. Just hang tight. Do you all agree with this so far? We're almost to the formula, all right? What I'm going to do is, let me see which way the book does this. I'm going to take this integral right here, okay? This integral right here, and I'm just going to move it to the other side of the equation, which means I'm going to subtract it. So it turns into this. U times v minus integral v u prime equals integral u v prime. You still with me on that? Just move this integral over by subtracting the integral on both sides of the equation. Yes? All right, now what I'm going to do is I'm going to just rearrange the equal sign. So I'm going to put the integral sign, this one right here on the left side, and then the left side now becomes the right side. It's kind of like if I write x equals 4, it's the same as writing 4 equals x, right? It doesn't matter which way I do it. So all I'm doing is just flipping it over. And now the last step, and we'll have the formula. I'm going to take, instead of writing primes, which meant derivatives, right? You probably remember in Cal 1 that at some point we wanted to always know what you were taking the derivative with respect to. So it was like, if I'm taking derivative of something with respect to x, it was like dx. Well, instead of just saying derivative of v, I'm going to write it this way. Integral u dv, that's going to represent this. V prime, I'm going to write as dv instead. And then equals u times v minus integral v. And instead of u prime, I'm going to write what? du. And this is the formula for integration by parts. Now you're probably looking at it going, what the hell is that? Well, that's the formula, okay? And there's a way to remember it. Anybody taught the way to remember it? No?
Just said remember it.
Okay. The way I was taught to remember this, I don't remember who told me this the first time. And I'm not a big fan of little cute things to remember things with, you know, but this one I think is actually pretty useful. Ultraviolet minus voodoo. Okay, ultraviolet minus voodoo. So this integral over here is equal to ultraviolet minus voodoo. Do you see it? Ultraviolet minus voodoo. Trust me, you can laugh. You're going to use it. At some point, you're probably going to use it. Okay.
On the test.
All right. Yeah, you can. What's up?
Oh, sorry, I have a quick question. Is this relatable to like if you were trying to find the derivative of x and y? And you know how they have the dx over dy?
Yeah, that's what this is. I'm just saying dv instead of v prime. But I still haven't shown you what this formula actually does, how it allows us to actually integrate something now. What I really want you to focus on in the formula, the equation, this integration by parts formula is this. Something that a very brilliant mathematician who taught me a lot was really trying to drill into my head when I was learning. He called this transferring, or the transfer of the derivative. That's really what integration by parts is. It's a transferring of the derivative. So let's look at this integral right here, all right? The way I want you to see this is that when I'm looking at this, this is multiplication, all right? I have some function u sitting there, right? U. And I've got next to it the derivative of some other function. See, dv, not du, dv. So I've got some function, and I have the derivative of something completely different. And integration by parts allows me to somehow transform this integral into this, which is just multiplication of two things, right? It's u, which is sitting right there, isn't it? It's v, which should be the antiderivative of that, right? But the new integral it creates, you may be saying to yourself, wait, I'm starting with an integral, I still have an integral, like who the hell cares? But what happened over here? The u in the new integral is actually what? Its derivative over here, and the dv that was here is actually what in here? The v, the antiderivative. So do you see how we transferred the derivative? The integral here, u had no derivative, v did, and we flipped it. In the new integral, v doesn't have the derivative and u does. Okay? Now, how in the world is that going to help us solve a problem? Let's see. Ultraviolet minus voodoo. So let's go back to this example that we started this whole thing with. X cosine x, oh no. Well, yeah, you know what? Let's just do this. Let's not do that. Remember how when we had the problem, it was like x cosine 5x? And then we reduced it down and got it to what? U cosine u, right? So this would be the same thing. We were still stuck on that, right? So we know substitution doesn't work here, right? So let's see how integration by parts might. And I'm going to put the formula over here until you memorize it. Sometimes I forget the first integral. So the way I remember it is I say in my head ultraviolet minus voodoo. And if this one's voodoo, then because the transferring derivative, this should be the opposite over there. So instead of voodoo, right, do is du, so I should just have u, and instead of v, it's dv. I don't know if that makes sense, but no? Yeah. There's the formula. So what you need to identify in here is something and then the derivative of something else. But more importantly than seeing something in the derivative of something else is understanding whatever you pick for u here, what's going to happen to it over here? It's going to be its derivative, right? So what you pick over here, be smart about it. Pick something that perhaps when you take its derivative, it becomes nicer than what it is over here. Right? Like what could I pick over here that when I take the derivative of it, over there it would be something clean? X, right? If I choose this right here to be my u, then in my new integral, what's it going to be? A 1 dx. Right? But that means I'm forced, if that right there is my u, everything else in the problem is my dv. Everything over here is dv. You see that? And what am I going to have to do with that dv over here? It's going to have to become v, so I'm going to have to integrate it to get back. Now, can you integrate cosine x dx? Yeah, what's the antiderivative of cosine x dx? Just sine x. Do you see that? Okay, so let me follow through this. I see some of you falling asleep. You can get up, go walk around, go run up and down the stairs. You fall asleep, I'm kicking you out. Okay? So wake up. So this is the standard way that I do integration by parts. I start with the table underneath. All right? You seen this now? You remember this? No? Okay. I start with the table, and I put u here, and I put dv here. I should always know those two to start the problem. I have to pick them, right? I have to pick the u, I have to pick the dv. So what did we pick in this problem for our u? X, right? And what are we picking for our dv? Cosine x dx. You got to pick the whole thing, right? And now what I'm going to do is underneath, I'm going to take the derivative of u. What's du? I'm going to put that right here. Du is 1 dx, right? So it's really 1 dx, or just dx. So I picked my u, I differentiated down to get this. I picked my dv, I'm going to integrate up to get my v. Do you see how this is going to work? And I'm going to have a table at the end that's going to have u du and v dv. So to get v, I'm integrating this, which is sine x, right? Now you could say plus c, but we're going to get a plus c at the very end anyway. So I'm not even going to put it there right now. With me? So this new integral right here, and I'm basically going to say equals because I still have everything in terms of x, as you'll see. What's the first part of the integration by parts formula? If I had u dv, it becomes equal to what? uv, right? That's u, which is x, times v, which is sine x. So x sine x, right? That's u times v, minus integral of v, which is sine x, crap, I'm off the camera. Sine x that's v, du is dx, so dx, right? So I'm going to get rid of this table so I can get it all on one frame. So what we had here was x sine x minus integral sine x dx. And what's the antiderivative of sine x? Negative cosine x, right? So we have x sine x minus negative cosine x now plus c, okay? Which is x sine x plus cosine x plus c. There it is. So do you see the power of transferring of the derivative? You have something that had this x that was causing all sorts of problems for us, and by integration by parts, you're able to actually just eliminate that x from the integral. But you had to be able to come back up from this and be able to integrate it up to get a sine x. Yes?
So when we're done with that, we would just re-put in the u's of what once they were?
No, because our answer has x's in it. So this isn't technically a substitution. It's really just a matching the u's and the v's to the formula.
Well, it's the original function, though. We found the substitution for the first part of it.
Oh, yeah, no. Let's look at this as its own problem. Let's forget what I put on the board earlier. Yeah. This is this is the beginning of the problem, this is the end. If we started with the other one, we would have had to have put everything back, yes. All right, now I want to do a quick check just to show you that this does work, okay? That this answer should be the antiderivative of this. That means if I take the derivative of this, I should get that, right? So watch, let's do this derivative, and I'm just going to squeeze it right in here. I have two terms, right? What is the derivative of this first term? What rule do we have to use there? Product rule, right? There's a product right there between those two. So product rule would mean derivative of x, which is 1, times sine x, right? Plus derivative of sine x, which is cosine x, times the x. And then what's the derivative of cosine x? Negative sine x. And then derivative of our constant is 0. What is that? X times cosine x. Right? You see? It works. I mean, do you know what I'm saying? Like, when you look at that, how in the hell would you ever come up with that as an antiderivative just by looking? You see? It's so hard to undo products with integrals. It's so difficult to do it. It requires something special like this technique. That's our first example. What do y'all think of it? I erased the formula, damn it. So what I'm going to do is I'm going to work through some even problems today. That way you can do odds. I'm going to start with well, yeah, let's start with this one. I'll start with 6. Integral x minus 1 sine pi x dx. This is very similar to the problem we just did. Now, your instinct might be to try substitution first, okay? And this, look, this is where things start to get really, really complicated because we had substitution, right? That's what we talked about before. So you knew every problem that I gave you, there was some substitution that should work, right? Now this new technique has shown us that sometimes substitution does not work. So integration by parts might work. And then there's going to be another technique that we learned 6.2. And then there's going to be a 6.3. And so we have all these techniques. And so by the time you get to like a big test, you look at an integral and you have to figure out what you're going to do with it. What technique are you going to attack it with?
Is there one technique that'll work no matter what?
No. It's called, there are the techniques of integration, plural. If there was the la technique, then a singular, that would be beautiful, but there's not.
Is the test going to be like separating sections? Like,
I haven't decided yet. I think your first test, which is coming up pretty soon, is going to have it's only going to have substitution integration by parts. So I'll probably prompt you in the problem, use substitution to find this, or use, and then maybe give you, but remember I said I might have an A level, B level, C level. I may not, I may somehow make the A levels where I don't tell you what to do. I don't know yet. I haven't put it together. Okay, so substitution we could try, right? It's not going to work, and I'm not going to invest time showing substitution doesn't work here. I'm going to go straight to it. But you know what? When you're looking at this, you don't want to, like every problem, be like, here it comes, substitution, take a big swing. Yeah, substitution. If you see the transferring of the derivative now, then go with integration by parts. If you see a u dv that you like, then try it. So what would you want to choose integration by parts? What would you want to choose for your u, and what would you want to choose for your dv? All right, we need to pick a u and a dv. Sine pi x for u, and then what's the derivative of that? Look, everyone, let's follow this. If we pick sine pi x for u, then over here, what will be du? The derivative of that, right? Which would be cosine pi x times pi, right? Because chain rule. But that would force us to pick the x minus 1 as our what? As our dv. And so the antiderivative of that would be what we need over here. What's the antiderivative of x minus 1? 1/2 x squared minus x. That looks like it just got a little more complicated, didn't it? Right? So why not choose the other way?
choose pi x.
Choose your x minus 1 to be your u, your sine pi x to be your dv. That way, when we transfer the derivative from the u, it'll now become derivative of this, which is just 1 or dx, right? So you're wanting that transferring the derivative to create something cleaner, not something more complicated, at least for now. So here's my table. I'm not going to make it as big this time. U is here, dv is here. I'm making my choice. And hey, look, if you make the wrong choice, you crumble up the piece of paper and you start over, all right? And you pick a different u and you pick a different dv and you go for it. Any questions on that part right there? Now I'm ready to go with this. What's du? Dx. And what is v? So you've got to be able to integrate some stuff now. Now, I mean, let's really appreciate this. To integrate this, you have to do a substitution, right? A little mini substitution. U is equal to pi x, and do a little mini sub, because you're going to be off by a constant. So I'm not here to show you how to do this integration from here to here anymore. This is something that you should be able to do. That's 1 over pi cosine, negative 1 over pi cosine pi x. Why did we need the negative? Because the antiderivative of sine is negative cosine. Why did we need the 1 over pi? To kill off the pi we're going to get from chain rule when we take the derivative of this. Because derivative of pi x inside would give us a pi at the end over here. but we got to kill it, so we put a 1 over pi in front. So can you appreciate the amount of work that was required to go from here to here? So you might need to, like, you know, on separate paper, scratch paper, make that its own problem. It would have been this, right? And you go through and you work that problem out. And once you get your answer, it's right here. Now that's just one little piece of the bigger puzzle here. See, I wasn't kidding when I said this builds on itself, right? I mean, I'm being truthful. All right, so we're ready for ultraviolet minus voodoo, right? This becomes ultraviolet. This times this, right? Yes?
It's product rule, right?
What's product?
Like to get the negative 1 over pi or what?
This is integration to go up. We're integrating. It's that integral. It's the integral of this. So imagine if I integrate this, right? If I take the integral of this and the integral of this, the antiderivative of dv is v. The antiderivative of this is this. So this is like a problem you would have seen on 5.5. One of the first problems on 5.5. You'd have to do a basic substitution. You'd probably do u equals pi x, du equals pi dx. I have dx. I need to get rid of the pi, so I go 1 over pi, right? You see what I'm saying? That's what you would have to do to get from here back up here. Ultraviolet minus voodoo. What's ultraviolet for us? This times this, right? So watch the way we're going to write that. It's going to be negative 1 over pi x minus 1 cosine pi x. So that's just ultraviolet, right? Ultraviolet. Minus, I'm going to run out of space, so I'm going to put it right here. Minus integral voodoo, v du. So it's going to be these two, right? So negative 1 over pi cosine pi x dx. And I don't need that, that negative 1 over pi inside. I don't necessarily need that in there, right? I can factor that out. So here's I'm just rewriting this. 1 over pi x minus 1 cosine pi x. That was my ultraviolet. Minus voodoo now becomes plus 1 over pi integral cosine pi x dx. That's where we are. Can you find the antiderivative of cosine pi x? Well, you might have to do a little substitution problem on that if you're not comfortable with it yet. What's the antiderivative of cosine?
Would it be just
Sine, 1 over pi,
sine of it?
sine of pi x, correct. Yeah. You want to start seeing that way. That's the way you want to start seeing it. In general, look, if you ever get this, check this out. I don't like formulas. I like people to understand first, but if you want to ever take the antiderivative of cosine of a constant times x, it's always going to be 1 over a sine of ax plus c. You always have to scale it by whatever constant's in here. And then if you have the other integral where it's sine, then you have to scale it by negative 1 over a, because the 1 over a will kill off that a, and the negative is just the fact that the antiderivative of sine is negative cosine. So if you like formulas, there you go. All right, let's do this. This is negative 1 over pi x minus 1 cosine pi x plus, no, wait, yeah, I'll do plus 1 over pi times, now what was the antiderivative of this? 1 over pi sine pi x plus c. We're done. I mean, we can put these pi's together right here. We can say 1 over pi squared. That's about it, though. That's the answer. You can check it yourself if you'd like by taking the derivative.
I trust you.
Yeah. I need to stop this real quick. How do y'all feel?